time our recording. So now now we are discussing the so-called PID controller, okay? And we will be keeping discussing PID controller for a while, okay? We will start with basically our approach in 302. So we will try to remember how we can kind of understand what these different modes, the proportional, integral, and derivative modes contribute to the behavior of the controller. And then later on we will derive design equations that would basically give us a way of calculating a suitable PID controller for a given problem. Okay. Now what is the PID controller? The PID controller, I will write it down in the time domain. Let's maybe pick up a different color. Okay. So we are actually calculating the output of the controller as a function of the error signal. Now this starts with a bias term. This is really our operating point, okay, UOP. Remember that often we need to linearize the system, either linearize the system or take care of the initial condition. And in order to do that, often the control input, the U of t, the output of the controller, varies around a constant value, okay? So on top of that, we have a coefficient Kc times the error itself. This is the proportional term, okay? This is the proportional term. And then we have Kc over tau I times the integral of the error, okay, 0 to t, E of t dt. That is called the integral term. And we also have a derivative term, Kc tau d times dE of t over dt. And this is the so-called derivative term. Okay. Obviously, if you assume equilibrium operation around the equilibrium point or the operating point, the initial conditions will be 0, and therefore you can also transform this into the Laplace domain, which is something that we are familiar with. Okay. Now, what you are not familiar with is that, in fact, you see the coefficients here are kind of interesting. Okay. You see that Kc here is actually used as a common term in all the coefficients for both, the proportional term, the integral term, and the derivative term. Kc is a common factor. So you can, in fact, take it out of, you can take it into Kc parentheses. Now, this brings us to the so-called forms of this PID controller. This is in particular called the dependent ideal PID form. Okay, so this particular parametrization has a name and it's called the dependent ideal PID form. Now, why is that so? Is mainly because of different ways the PID controller is implemented in the industry. People have implemented different parametrizations and they have given these names for them. And if you ever use a commercial PID controller when you will be working in industry, let's say you will have a device which comes with its controllers and there is a user interface, it becomes important to notice in what form the PID controller is implemented. Okay, because you will often have fields where you will fill in the design parameters in order to implement the controller, and that really depends on what those parameter means. I mean, if for example this is parameter 1, this is parameter 2, this is parameter 3, okay, so these are controller parameters. I mean, if you notice that it is a dependent ideal PID controller and it has 3 parameters, these are the parameters that are required, okay? Or the interface might ask you to simply enter the proportional gain and the integral time constant and the derivative time constant. In this case, this is what is meant, okay? So you see that P1, P2, and P3 coefficients are determined by the Kc, tau I, and tau d parameters. Okay, so let me make a note here of what I've just said. Okay, the definition of the PID controller becomes particularly important if you are using a commercial controller with a graphical user interface. You can encounter different definitions, and I will now list some of the other definitions. It is important to note that these different definitions does not fundamentally alter the nature of the PID controller. It's always the same. It is always the same type of controller, and it's always the same kind of performance that you will get from this type of controller. Okay? What is changing is only what are the names of the parameters and how they enter this equation. Okay? So we have defined this so-called dependent ideal PID. What is above? We have other definitions that you might hear or come across. One is called the dependent interacting PID. And I will make the definition now here. Okay, so in this case, U of t is again U bias plus an interesting combination of the parameters, Kc times 1 plus tau d over tau I times E of t. So you see that all parameters somehow affect the error here, plus Kc over tau I times the integral 0 to t E of t dt plus Kc times tau d dE of t over dt. Okay, so that is the dependent interacting PID. And another one that you will be familiar with is the so-called independent PID. And that is simply U of t is given by, again, U bias plus simply Kc times E of t plus Ki times the integral of E of t plus Kd times the derivative of E of t. Okay, maybe this is kind of the most familiar one for you. Okay. Also, sometimes you might come across another term. Instead of KC, a so-called proportional band is specified. And that has direct relationship between Kc and this band. Basically, Kc is equal to 1 over Pb, okay, where Pb is the proportional band. Okay, so this is other weird terminology. Okay. What is important to note is that all PID forms have essentially the same performance. So it's not, we are not talking about a different type of controller. We are just talking about a different parameterization of the same controller. So the names of the parameters changes, but essentially it's the same type of controller. Okay. There is another issue with the PID controller that that is new for us. Let's call this the derivative of the error. Okay. Now, the note is that the derivative of the error often behaves let's say numerically problematically. What I mean by that is that when you take the derivative of the error, okay, let me give you an example. Remember the structure here, right? We have a difference of y of t and the reference r of t. And this is our error. Now, what if, let's say, if the reference r of t actually is a piecewise constant signal. So you get to R1 and you get back to 0, okay? And let's say the output is a continuous waveform, because it often is. Because this is the output of a dynamic system. Often there is a bandwidth to the system. So independent of what's the input to the system, the output will behave smoothly, okay? So let's say the output will basically is a signal like this. So what is E of t? E of t is R of t minus Y of t. Okay? So what's going to be E of t look like? E of t versus t. So this is the reference, okay? So it's going to be reference minus y of t. So it's going to start with a signal like this. And then r of t will go to r1. So it's going to jump to some value. And then will continue. And then it's going to jump back, I don't know, somewhere here. And then will continue, okay? So there will be discontinuities. Now, what is the problem with discontinuities when you take the derivative? Over here in these points, derivative, at least the continuous derivative, is undefined. Derivative undefined. What's going to happen is that at these points, the derivative will have impulse functions. Okay? So that means if you take the derivative of the error, if you need that, and this is the behavior of the reference signal. In fact, dE of t over dt is a problematic signal. Okay? Because of the discontinuities. Okay? Because of discontinuities. Continuous, let's say E of t. Now let's take a look at this derivative. Okay, so we have E of t equals R of t minus Y of t, and the derivative of E of t therefore is equal to dR of t over dt minus dy of t over dt. Okay, now dR of t over dt is almost zero except for discontinuities. Okay. So apart from those very infinitesimally small time instants where the value of dR of t over dt is non-zero, it's zero everywhere else. At least for piecewise constant, R of t. In this case, we can assume dE of t over dt to be approximately equal to minus dy of t over dt. And this derivative is much better behaving because of continuous differentiable system output. Now, why I'm discussing this is that often in industry you will find that instead of the derivative of the error, you will find that the PID controller uses the derivative of the output. Okay? So often you will find derivative of the output used instead of the derivative of the error. And that's the reason behind it. Okay? So what we have is that in this case, U of t with this new definition is U bias again, plus again using this dependent ideal PID form. Okay, so we will have Kc times E of t plus Kc over tau I times the integral of the error E of t dt plus, instead of a plus, now I will have a minus Kc tau d, and instead of the derivative of the error, I will have dy of t over dt. Okay? So you know, if I sketch the block diagram now, you might argue that this kind of changes the architecture slightly, because here you see I have the reference, I have the error signal, and I have the controller, which is our PID controller this time, and plant or process the output y of t, u of t. Now in this case, instead of just using the error, you have something like this, right? You have basically an S term here, okay? In fact, not an S term, but a minus S term. And then this goes in to over here, okay? Inside the controller. Okay, so that's another note about the PID controller that you will come across, right? I guess we can have our session exercise at this point, and then I will continue, okay? So let's say session exercise. Dersin sonuna sıkışmamak için şimdi yapalım isterseniz. Hepiniz hazırsanız şeye geçebilirsiniz. Metü Class sayfamıza. Bir saniye. Alright guys, so let's move on to our session exercise. I will make it visible now. Here we go. Okay, so I'm starting the session. If you reload your browsers, it should be available now. Hayattasınız değil mi arkadaşlar? Hiç ses gelmiyor.
Oradayız.
Tamam, süper.